All right, welcome back. Now, on Monday, we had gone through and talked about pressure vessels and press and shrink fits, and we introduced the homework problems for that set. All right, it's a fairly plug and chug type chapter. We're now moving toward the last little bit of material, which is going to focus on energy methods and then thermal expansion and buckling. So today we're going to dive into energy methods, get the whole X-Men Origins Wolverine backstory for that, and look at a few applied problems. Then we'll take a little break from that next week. We're going to review the torsion and axisymmetric. I realize we only have about a week on that homework set, but it's very quick plug and chug type problems. So once you set up the formula in MATLAB or MathCAD or Excel, you can just plug and chug and copy and paste for the problems down one. We'll just change the ink. All right. So next Monday, we're going to review torsion and our pressure vessels problem sets. And then we're looking to do an exam next Wednesday. It's going to be on those two topics. All right. Same format as before, same everything else as before. I do have your exam number one results. We have two people that haven't taken it yet. So I'm going to leave that toward the end of class. We'll just talk about it in general terms. But everybody did real well, so nothing to worry about there. Then we got Memorial Day the following Monday, Wednesday the 27th. So 2 weeks from today, we're going to jump back to energy methods. We'll look at virtual work and this Rayleigh-Ritz method. If you don't like free body diagrams, this will be your time to shine. Then in our last main full week of class, we're going to talk about thermal expansion. So that alpha delta T that we touched on back in the strain chapter. And if we don't allow expansion relief, what kind of loads does it build up? Also, how much temperature change does it take to cause buckling? So we'll look at mechanical and thermal buckling. We'll do a little fleet issues where we'll touch on some current and near past issues affecting the fleet that relate directly back to our topics. That one will be for U.S. students only. And then Monday the 8th, we'll review homework number 5. So right now, assuming we don't slip on pace and we're doing pretty good, we'll probably look to be finished around this 10th to 11th as our final exam period. If for any reason something slides around a little bit, we're going to hold Monday in reserve. I'm pretty sure we won't need Wednesday, 17 June at this point. So I'm planning on finishing us up on the 10th, maybe 15th if we need to slip. If you do have any classes, more for the resident folks, if you have any classes on Tuesday, this is going to be the faculty retreat. It's not really a retreat. It's just over to the municipal pier, but there won't be any classes. Doesn't affect us, but just so you're aware, there won't be any classes for anybody in MAE on Tuesday tonight. So that shouldn't affect our pace, but in other classes, you may see it slide today. So that's our plan for the rest of the quarter. Yeah.
If some of us have travel that we're trying to get everything wrapped up before the week of the 8th, is it possible to get the exam before that?
Yeah, that's fine. So if if that's also a significantly few people, I can swap this and this slide set. You can still watch this later. It'll be on Teams instead of Zoom, but I can slide this over here and this over and this down here, sort of deal. If there's folks, we can do this. I was a little bit hesitant to do that because the last stuff is going to be would be a couple days before it and the last of the topics. But if we get a little bit ahead, but I could do something like that, or I could give you an individual review and then you could take the test. So something along those lines. We can work something out for that.
Just like before that.
Yeah, I mean, I can get it to you, no problem. We'll just need to schedule some sort of review time or something like that. I didn't want us to be in too much of a rush because the last of the stuff you need for homework 5 is in this 1 June lecture. So, we can work that out. All right, so let's dive into today's topic, which is going to be energy methods and looking at that strain energy as a property. So when we think about energy, we go back to maybe high school physics class. We had kinetic energy and we had potential energy and we had work, right? And there was that old expression, delta KE plus our change in work, change in energy had to sum out to zero for conservation of energy, right? So we'd say that delta of kinetic, which was, if we had a half mv squared kind of thing, and then there was a delta potential energy, that was usually some kind of mass times gravity times height, like a height potential. But that could also be a spring potential. Like if we stretch out a spring, it's holding some energy. And then some external mechanical work on a system, delta work. Does this ring a bell back from high school or college physics? Conservation of energy, essentially. Right. And in our solid mechanics models, we have a conservation of energy. We do some work on it via applied and external loads, and that energy is stored in the form of deformation and strain energy like this. So when we think about strain energy in a solid, we apply some load to it and it displaces. And we usually ramp that load. So we pull on something with additional load, it'll stretch out farther and farther along that elastic slope, right? And the area underneath this curve is our strain energy. That goes toward this potential energy. It's a stored or strain type energy, all right? So force by displacement, we go up that curve to some applied loading, and we've displaced a certain amount. Here's the energy that we're holding. Force on one axis, displacement on the other. So the area under this curve is an energy value. Now, if we think in terms of our smaller scale on solid mechanics, I've got force and I've got displacement. If I take that force and I divide it by some cross-sectional area, all right? So let's say we're talking about a cylinder here, and it's got some load P on it. It's got some area A to it, and it's got some length L, right? And it's going to displace up some distance delta as we apply this load. So that's what we're seeing going on here, force and displacement on this graph. If I divide by that cross section, I get stress on this axis, right? And then if I take displacement and I divide that one through by the length, I can get a strain here. So this is stress strain. This is like what we talk about with our elastic and plastic behavior. If we're going up the elastic behavior, the slope of this is Young's modulus, right? Looks just like this. And the area under this curve also represents a form of energy, but it's an energy per unit volume. It's called strain energy density over here. Usually it's going to be a lowercase u for this one and a capital U for this strain energy over here. But strain energy per unit volume. We took a force per area, so now we're per area. We took our displacement and did it per length, so now we're times length. And I could see A times L gives me the volume that was inside. So on the macro scale, in terms of energy, we think about load versus displacement. If we want to break that down into something that we can do inside the part in an individual spot, I can do stress versus strain. And that is also an energy, but it's an energy divided by volume. A times L is on the bottom. A on one axis, L on the other. So this area under here is energy per volume. We just integrate it up per volume. Now, if it's a axial bar like this and everything's constant, then I just multiply it back by A and L and we get back to strain. If it's bending, let's think about bending. The stress changes through the body, all right? As we go up and down that y-axis, the stress changes, all right? So we're going to look at how to set up this strain energy density and then how to integrate it up to get a total energy for, say, a bar or a beam or a torsional member. So figure out how to do strain energy axial bars. We've done that. Beam bending, shear, transfer shear, and then torsion of prismatic bars. We'll talk about the Castigliano theorem, how to use Castigliano for both determinate and indeterminate members. And then probably later on, we'll get into this virtual work and Rayleigh-Ritz method. That'll probably be, like we said, a few class days down the line. So this is going to be a slightly different approach. It's a scalar approach in that energy doesn't have a direction to it. We're adding up a total value. It's very useful for cases where we have a complicated amount of geometry, maybe lots of pieces to put together. And if we were going to try to use our differential equations approach and add up all the displacements and movements, it could be difficult. If we take an energy approach, we just add up the total energy, and then our Castigliano method will allow us to get some deformations just based on that single energy. Also applies for some linear and nonlinear cases. We might have a material nonlinearity, that is, the stress strain curve is not a straight line. That's the case some materials like rubber. They might still be elastic, but they don't follow that path. And then geometric nonlinearity is large displacements or large deflection. So energy methods can handle both of those types. So just like we drew out in the opening slide there, we think about strain as or strain energy as a load by a displacement, and the area under there is that multiplication. Load times a length, force times length, that's energy. And here we went force per length squared, and then we went length per length. So we still have a force times length in the numerator, but we have length cubed in the bottom. So there comes the per unit volume. And these curves we can go back and forth between if there's a constant stress and a constant strain. Now we get into the beam bending, that varies by the location in the volume. So we'll have to integrate up rather than just multiply. But we could see a direct relation between these two. One's a type of energy, but it's per volume, and the other one is a total energy. So let's talk about this Castigliano theorem. This is a way that we can figure out deflections in bars, beams, trusses, lots of different members. We can calculate horizontal, vertical deflection, and also rotation. So we can combine axial bar and beam bending effects. And there's two different Castigliano theorems. All right. Basically, in each of these, we need to know what our strain energy is going to be. All right. Like I said, we'll call that one capital U. Now, in the first Castigliano theorem, what I say is if I've added up all of that energy, and let's say that I formulate it in terms of displacements, I could say du, partial derivative of u with some displacement where a load is applied will give me that force. Right? So if I've got some blob here, it's got a support back here, and I got some loads on it. I got a load, change the color for that. Let's do red. So I've got some load here, got some load here, and I want to know what load is required to perform a certain displacement. So right at this spot, I've got some displacement delta. I add up all the energy that's inside here. That's my capital U. Then I take the derivative of that with respect to displacement, and it'll tell me what force is required to do that. Right? Now that requires us to formulate everything in terms of displacements. That one can be a little bit tricky to do, but it can handle both linear and nonlinear materials because we're basing everything just off of the geometry. Now, the second one is going to be for linear elastic materials, and this is the one that we're going to try. It's just the reverse of that. It says if I add up all the energy from forces and I calculate it based on forces, so my energy is a function of the loads, I can say du df is going to be equal to the displacement. So just swap the place for that force and the displacement. So if I got a bunch of loads on a body and I add up the energy, this could be a truss with a bunch of structures, lots of different members in there. It could be a blob, but I got some loads on there. I add up the energy in terms of those loads, and then I take the derivative with respect to one of them. This load right here, capital F. That derivative will give me the displacement at the same spot and in the same direction as that load. So the sign convention is whether this comes out plus or minus. If it's positive, it's going the exact same way as the force, right? Now, if there's a bunch of loads and it's still moving back the other way, despite the force pulling there, we'll just get a negative for this one. But all I need to do to get this is solve how much energy is in here and write it out in terms of the loads. So this is the basis for our energy method, our Castigliano theorem. So there it is in formal terms, and we can do this for as many places as there are loads on the body. So I can get it at F1, I can get it at F2, I can get it at F3, etc., etc. I can even get it somewhere where there's not a load by putting a dummy load on. Talk about that a little bit later. Okay. So I put a load in there, I solve for the energy, and then later I set it equal to 0 after I've done this. So we can use this to find displacements. Oftentimes we want to know what's the movement where we apply the load, and we can even use it to find stuff where we don't have a load, right? Likewise, that F sub I and delta sub I applies in the general sense that we're talking about some sort of geometric movement that we're solving for in terms of a load. That also includes rotation and moment as a pair, all right? So if I formulate the energy and I've got a concentrated moment at some spot, I can take the energy derivative with respect to that moment, and I also get the rotation. The rotation is in the same direction of the moment that was applied. Right? So back here, if I've got it in terms of this F over here, I can also get, say I've got a moment and it's sitting right over here. I can get the rotation at that spot like this. It's going to be in the same spot and the same direction. By taking d energy, d moment, I get the theta at that spot. So this works for force and the displacement at that spot, also works for a moment and the rotation at that same spot. So in the general case, we got some structure, we'll just describe it as a blob here, multiple loads, they could be forces, they could be moments, and then we get some geometric output, displacements for forces, and we get rotations for moments. All in the same spot and in the same direction as that one that we're taking the derivative with. So we see that delta 3 and F3, same spot, same direction, etc., etc. So let's think about the simplest kind of body we can think of is a linear elastic spring, right? And for a spring, I can formulate it in terms of displacement. I could formulate that spring energy as a half of K times delta squared. And here's my spring Hooke's law, right? Force equals K times delta. So I can also put it in energy as a half of F squared over K. Now this one is such a simple strain energy diagram that we really don't need the Castigliano theorem to figure it out. This is one where I've got some applied force here. I've got some displacement delta, and my slope along here is K. Right? So without a whole lot of work, I already know that the relationship between F and delta is F over K equals delta, or F equals K times delta. But let's make sure that this checks out for the energy method. So here's my triangle. That's made up of 1/2, because we've got a triangle area underneath. So we got that half. And then F times D, and I want to set it up all in terms of load. So delta, I'm going to put in F over K. So I got a half times F over K. Goes right here. 1/2 F squared over K. Here's my energy formulated in terms of that force. And if I take partial U, partial F, sure enough, the 2 comes down, takes care of the half, and I get F over K, which I know is my spring. All right. So for the simplest member that we have, which is an axial spring, we already know the answer for that one. It's pretty straightforward. Delta is F over K. And if I formulate the energy like this, I see it does come out. I take the derivative with F, the squared goes off and cancels the half, and we're left with F over K. All right, so everybody comfortable with the Castigliano? We've seen it in the absolute simplest case right here. Any questions on that? All right, now let's think about a bar with axial loading. All right, so here we've got a bar, constant applied force on each end, and that means no matter where we take a slice through this thing, going to be F over A for our stress there. All right. So we're going to flip back and forth between 1 and 1A here. Here's our axial bar, stress F over A, epsilon, our strain, F over AE, because it's sigma over E. All right. And we said that if we go to our little strain energy density, that's this one right here, half of sigma by epsilon. If I'm looking at strain on this axis and I'm looking at stress on this axis, the area under this curve is energy per volume. And so I need to go d volume with that. All right. So we need an expression for both of these things in terms of force. And we've got it, right? F over A, and then epsilon is sigma over E. So I can do F over A and just add an E on the bottom. All right. So I'll put that in there. I get F squared over 2A squared times E. And then because this one is a constant, we can break that d volume, stress constant and strain constant. We'll break that d volume into a cross section, d area, and a length dx. Right. So we're going across the area dA and from 0 to L dx. Well, none of this stuff in here, this is all a constant with the area, so we can bring it out. And integral of dA is just area. So notice one area comes up and cancels one of the areas on the bottom. And then lastly, we've got the dx. Well, none of this stuff changes along the length either. So that can all come outside. And we can get, for a constant force, area, and modulus, we get a half F squared L over AE. So if everything's a constant, it comes right out like this. If any of these things is a function of X, all right, so let's say we have a bar with there's a load in the middle. I just break it into two pieces. I'll have an F1 and an F2, and they'll each have their own length and add them up. If there's a distributed load, F becomes a ramp function. So we have any of these things that change. If the bar changes, the load changes, or the material changes, we either break it into pieces or we leave it inside as a function. The one that usually changes is F. We have a distributed load, F is a ramp, or maybe we have a tapered bar where A is a function of X. So anything that's not constant will stay in here. This is always good. But if we have everything constant, it just becomes F squared over 2AE times the length, because everything comes out and we got just integral dx. All right. So most of the time we will be able to use that shortcut one over there. Every individual bar that doesn't have a load in the middle, we can use that left-hand formula. And if anything's changing, we just keep this. Let's take a look at a torsional bar next. Probably the next simplest one to look at. Now, in this case, we're not going to look at sigma versus epsilon. We're going to look at gamma versus tau. But it's still elastic, and it still has that linear behavior like this. What's our slope between tau and gamma? What's the Hooke's law there? All right, I know it's late in the afternoon. Just shear modulus, right? So we got the same kind of curve, but it just goes up with a slope of shear modulus. Tau equals G times gamma, right? So tau, we know TR over J. That's our polar moment. our torque and our radial position. Gamma, tau over G, so TR over GJ. And here's our strain energy formula. A half tau gamma, that's strain energy density, stress versus strain, and then we're still going up per volume. So we put tau and gamma together, and the 1/2, we get a tau squared, torque squared, T squared, 2GJ squared on the bottom, and we got an integral, or we got an R squared on the top, right? Everything but R can pass out from the cross-sectional area. Radius does vary if I'm taking a slice of the cross-section, right? Here's my D area, is I need to integrate up all the little pieces of this. Well, torque's the same between there and all across there. G's the same, J's the same. Those properties don't change across an area. But along that green slice we just drew, radius is different in different parts. So we're going to leave that in there. R squared dA. Well, we've seen that before. That's just J. So J comes out, and we see it cancels one of the J's on the bottom. Well, coincidentally, that's what we just did up here, right? We had integral D area, got us an A on the top, and it canceled one of the A's on the bottom. And then, assuming all this stuff is held constant, we can pull it outside. So we got integral dx, 0 to L, T squared over 2GJ dx. If everything in there is constant, and it's often the case for a torsion member, just T squared L over 2GJ. Right. Here's this one. We can usually use this one. Rarely do we have a distributed torque, right? So if I just break the bar to pieces in between the applied torques, I can most often use that. On the rare case, there's maybe some sort of a frictional bearing pack that provides a torque per length and torque changes as a formula. Or if we have a tapered bar, tapered conical shape, J might change. Rarely is G smoothly changing. It's usually G1 here and it's G2 there. So just break it into some pieces. So this one we can often use everything's constant and set it up like that. We should be seeing kind of a common theme between these. We got a load squared on the top. We got a half. We got a material property and a geometry or cross-section property there. So T, G, and J. Before we had force, there's our load. There's our material property E and our cross-section property or geometric property of area. So we're going to see those same kind of things as we go through. Let's take a look at beam subject to bending. We do know M is often M of X, right? So this is the one where most of the time we're going to have to use this one, all right? E and I will probably still come out. So we'll just be left with an M squared integrated. It's usually some kind of polynomial, and we got to FOIL it out. So not too bad. But this one, I want to caution you, we can only use this left side when there's a constant moment, and that doesn't happen as often as the other. So let's see how we come up with this one. So for beam bending, here's our formula, my per I, and our epsilon, just sigma over E. Bending is still 1D in terms of the Hooke's law. We're only really looking at sigma XX and epsilon XX. So again, we're still in a 1D type case there. So a half sigma epsilon, we're still going to be going up and down linear stress strain curve right here. But unlike the other cases where we had, unlike the axial where it was going to be the same all the way through, ours is going to vary by Y location, right? We saw that is basically in the formula. So like the torsion, it varies with some cross-sectional location. So here's our beam. Let's just say we're looking at a cross-section slice like this, all right, rectangular cross-section. So as I go up and down it, my stress is going to change. So I throw these in there. I've got a M squared, Y squared, 2E, and I squared. E, I, and M are not a function of change across that green slice we just drew. So they all come out. And what we're left with, y squared dA. We have seen that one before. That's our bending moment of inertia, I or IZZ. So that one comes out, and similar to the last two, cancels one of the geometry properties on the bottom. So we'll end up with an I in the bottom and an E in the bottom. We've got a load squared on the top, m squared, and we've got the 1/2. And very rarely is this moment going to be constant, because usually it's caused by some transverse load. So m of x is going to have to stick around. We can still pull out the 1/2 in the EI, and we'll just have to integrate the function for the moment. All right, we've made function moments before. We've done shear and moment diagrams. So m of x is not too hard for us to come up with. And we'll just have to FOIL it, square it, and integrate it out. Usually it's a polynomial for m, so it's not too bad to just do the chain rule going up piece by piece. So there's our bending energy for a beam of a given length with m of x distribution there. Usually we've got m of x, so we're going to have to keep this one inside. These guys on the bottom can usually escape out as a constant. All right, there's two more ones that we've got to come up with, transverse and direct shear. Now, I'm going to talk about the transverse shear one first. That's one thing we've been covering in the class, and then we'll hop on that direct shear one last. All right. So for transverse shear, we know that expression VQ over I times the thickness. All right, and that one is a function of how far down we go, because Q we have to shade, right? So for a given shear force, there's tau and there's gamma, and it follows the same as the torsional one. We're integrating 1/2 of tau times gamma. That's per volume, and then we need a d volume. So when I multiply those, I got v squared, I got q squared, 2i squared, a g, and then a thickness squared down there as well. So if I separate out things that are definitely not part of the cross section, doesn't vary as I go across it. V is the same across a given slice. G is the same across a given slice. And also I, it's made up of the cross section, but it's a constant value. And no matter where I am in there, I say that applies to the whole cross section. So that one comes out of the dA. What I'm left with, I've got a q squared in here, and I've got a t squared. The thickness, especially for something like a T-beam, could vary as I'm on the cross section. So that horizontal Z dimension, thickness in Z, and Q is what I shade down or up to, that integral y dA. That does vary with position on that cross section. All right. So Q and T I cannot get rid of. Even if it's a rectangular cross section, I go down, here's my width at some spot, and my Q is shaded from the top or bottom. So both of those vary over the position on dA. All right. If we look at what's in that parentheses, I've got an I squared down here. That's L to the 8th on the bottom. Over here, I got a cubed length twice. And then I got an L squared here. And then my area going up, dA, is also an L squared. So if I look at all the L's on the top, I got 8 L's on the top in this parentheses. So just talking about these geometric properties, and I got L to the 10th on the bottom. So that's L to the -2. Ideally, I wouldn't want to do that integral. I'd like to get rid of this, or maybe some combination of stuff where I don't have to calculate it. I can just look it up for the shape. All right. We like the easy button, like Staples commercials, right? So we need a unitless number, something we can just look up, and then no matter how big the shape is, it just depends on what it looks like. So if we need another length squared, why don't I throw an area in the side of the parentheses and also one outside? So I'll do a 1 over A and an A. Area over area is just times 1. So we'll put the A down here, and then we'll put an A on the numerator inside. Now, this whole bunch of stuff, which is really messy, is just a dimensionless number. We'll call that a correction factor. Right? So I got sum fudge factor times v squared over 2ag. Load squared, a 1/2, a cross-section or geometry property, and a material property, just like we had for all the others. And if we have a distributed load, V could vary, but oftentimes if we just have point loads, we could take this out. It's just going to be a times L. So this one, for transverse shear, we've got this formula, and as long as V is constant, it's just going to be times L like the other ones. All right. The only difference we see here is we got a little correction factor. We look it up. It's based on the shape. So a rectangle will have a specific shape. I-beam will have a specific number, and we can look those up in a table or provided those in a problem. So this takes care of shearing on a local scale where we've got that distribution of stresses. In large scale projects like civil engineering, we're often going to take a direct shear approach. This is something we don't see too often as an ME, but I'm going to throw it in there just in case you end up in the CEC at some point, or we're dealing with a really large structure. Some large sections of a ship, like the platform on, say, ESB, could be treated like this as a direct shear type. So the idea is, if we have a building or a platform, like a helicopter platform, and it's under some shear load, this could be due to wind or earthquake or anything like that, it gets a lateral load like that, right? We know that the ground underneath it has got to provide a reaction force like this. And in order for this to be balanced in the spinning sense, or moments out of the page, just like we have the tau for shear stress, right? When we see a pair of horizontal shear stresses like this, right on the top, left on the bottom, we also have a corresponding up and down one on the front and back face, right? So one of the assumptions we can do in a large civil engineering structure where we got some columns and then we have like a floor or a platform like ESB flight deck, which is just a floating platform on some stanchions. We've got some bars right here, and the way we can overcome this torque that's generated by the right and left hand movement there, that tends to want to put it clockwise. We put a counterclockwise couple right here. So there's a bar right here. This vertical column, we'll say, is getting pushed up. This one is pulling down. All right. So this one actually in tension, this one in compression. We're going to assume that these act, rather than as beams, we're going to treat them like bars. So if this thing wants to twist over to the right, if I push up on the right bar and I pull down on the left one, I could torque it back to the left. Torque it back counterclockwise. That would mean this one's going to be in compression, this one's going to be in tension. But at the end of that bar, that force gets passed on to the top member. All right. So let's take a look at this top member here. The reaction force that we had down here gets passed up through the column and pushes right here. And then on the back side, my reaction force down here is also pulling down on that column, and it's subsequently pulls down on that top floor or deck or platform that we have. Right? So this is a shear force that's generated to balance out the free body diagram, where we've got some applied force this way, and if we've got a box type section, it'll get passed through in the vertical to counteract. Right? This one will be a constant all the way across. Pull this out. F squared over 2 times A times G. Now, in the direct shear case, we assume that we have a constant stress. Okay, so it does not, like our solid mechanics approach and detailed ME approach, we try to make it 0 at the free surfaces and tapers. Here, we're just assuming it's F over A. So we don't enforce any free surface condition on the top or on the bottom. That means it's constant though, so everything comes out right away. Half tau gamma, F squared over 2A squared G. dA becomes an area, and we're left with F squared over 2AG dx. And that'll be constant along the length because the load is only applied on the ends. All right. So we can take this one right here. We don't see that one too often. but I like to introduce it in case anybody ends up down the civil engineering route. So we look at two kinds of shears. One is constant. That looks like a really short formula. Our messier formula that ended up with that correction factor is because the shear stress is a distribution, right? And that's what we draw here. Here's the transverse one. Because of that messy shape and Q, we had to have the fudge factor in there. Right? And if we have some structure with a combination of these loads, our linear superposition that we use back with the beams also applies to multi-axial loading. So if it's got an axial load plus a torsion plus a bending moment plus transverse shear or even direct shear, all we have to do is add these up. Very often in a beam, we're going to have some shear force creating a moment. We might have both of those. So everything could just be linear addition there, linear superposition of those. So any combinations of loads, we just add them up for a given. That also applies if we've got more than one member. We've got the same force passing through three different bars. We just add up for bar 1, for bar 2, and for bar 3. Right. So anybody have any questions about how we came up with these formulas? All right, let's jump over to our Castigliano slide set here, and let's set up an example. All right, we're going to look at a statically determinate structure. It's cantilevered, and we already know the answer to this one, luckily, so we can check our work back here with this 3.5 load cases. Right, we use some of those on the homeworks and etc. And here I can see for a force, I can look up that displacement, FL cubed over 3EI. So we're going to run through and we'll make sure that that comes out okay. So we got some load P here, EI and L, and we need to figure out the displacement using our energy method. So let's take a look and see how that comes out. We've got cantilever bar here, some load P on the end. I want to know, luckily, the displacement at the same spot down at the end there. And the beam's got standard properties, E, I, and L down the length. I've got some beam. Now, another good thing about our energy method is a scalar approach, right? So if I need the energy all across here, it's really not dependent on where I put things. I could have X over here as is customary, or if it's more convenient for me, I could put X right here. All right. The energy is going to get added up either way. So I'm free to pick where I put my coordinate system, make it easy as possible. So let's take a slice here. Now, if I put X over here, now I don't have to deal with an L minus X kind of thing, although it'll still come out the same. So I've got some P right here. So we're still doing a free body. Don't get to skip the free body till we get to the Ritz method. We've got an M of X. Also good for people that don't like to follow sign convention. I can draw my M and my V either way. Why? Because energy is a scalar. M squared, V squared. Doesn't matter which way you draw it. Okay? So if you don't like following sign convention rules, this is your time to shine, but you still have to draw a free body. I'm just going to lay them up the same way we've been doing them to be consistent. So let's V of X. I got V of X going up, P going down. So I can see that's just going to equal P. If I drew it the other way, minus P, but we're squaring V, right? So that minus goes away. Doesn't matter which way we draw these internal loads, all right? We're going to sum up moments. M of X would be our other thing that we need to find. I can see about this spot, M of X is going counterclockwise and P times X is going clockwise. So they're just going to oppose each other. I got P times X right there, okay? And now we're going to set up our U for the beam. I've got a shear, so I got some correction factor, V squared L over 2AG. V is a constant. I don't see any function of X in there, so we can use the shorter formula for that one, right? And then for my other one, I've got integral m squared over 2EI and a dx on that one. Okay. And here's where we're really happy that we put x from the end that we kept, because we don't have to do an L minus x. I don't have to FOIL anything. I just do a multiplication. All right. So U is going to come out C V squared L over 2AG. And then I could take the half EI right out and just integrate the m squared. So that's going to be p squared x squared dx. And that's going to be from 0 to L. All right. Note we're dx, so we just go over the whole length for the b. All right. Shear term still hanging around. And then here, I bring the p squared out. I've got an x cubed over 3. So a third's going to come down. That's going to make it 1/6 on the bottom. And then x is from 0 to L. So it's going to be p squared L cubed over 6EI. So here's my energy in terms of the shear and also in terms of the bending moment. All right. And here's my displacement on the end. I just say is partial U, partial P. All right. I want to know what the displacement is. I'm going to get that displacement at the same spot the load was applied and in the same direction. Right. If I'm pushing down, I expect that the beam is supposed to go down this way. So I should get a positive displacement for my number. Looks like I'm going to. So, my V squared is also just P, right? So I could put P in here for V, P equal to V. So C, P squared L over 2AG, and then P squared L cubed, because V and P were a constant, same value. Okay. So I'm going to get that fudge factor, PL over AG. The squared comes down and takes care of the half. And then I'm also going to get my square comes down, so I get P to the first L cubed over 3EI. And sure enough, there's what I get from the 3.5 slide set, right? But what about this? This wasn't on the slide set. Well, as we're going to turn out to see, the shear contribution for any long, slender beam is going to turn out to be pretty small if we throw some numbers in by comparison to the bending. So oftentimes people will omit this shear energy term. We do need that shear force on there because that's what makes our moment. But in terms of the energy value and the contribution to the displacement, we'll see that it actually is fairly small. All right. Anybody have any questions about how we came up with that one? All right, let's take a look. Throw a few numbers in there just to see what it looks like.
Yeah, I got a question.
Yeah.
So would you say that, in a sense, this is almost more accurate because you've got the extra factor in there?
Yeah, this will add a degree of accuracy because it accounts for the movement of this beam, not just from the bending, the M of X, but also from pushing down with a shearing force. All right.
Mm-hmm.
Now,
okay,
we're going to flip over here, and I want to demonstrate for a fairly short, stubby beam what kind of difference that makes. So let's look at a beam. It's 24 inches long, and we'll make it 3 by 1 inch. So this is a pretty stubby beam. The height to length to height ratio is only 8 to 1. All right, that's a very short beam. That's getting on the shorter end of what we'd consider a beam. Usually we expect it to be about 10 to 1 or longer. So we're at the very low end, 24 versus a height of 3. So it's just 8 to 1 length to height. All right. Moment of inertia comes out 2 1/4. And we'll put a load on the end of it of 100 pounds. All right. Fudge factors we can look up in tables. For a rectangular cross section like this, so 1.2 is going to be our form factor. For I-beams, it's the total area over the area of the web. And I think for a circle, it's 10 over 9. So there's just some standard numbers based on the cross section. For this cross section, we have a 1.2 fudge factor. These numbers are not terribly far off of 1 for your basic polygon shapes. For the I-beams, we've said area divided by area of the web. All right, so That one, depending on how skinny you make the web and how big you make the flange, number can go up a little. But it's something in the single digit neighborhood for most practical applications. And here's our E and our G. All right. So if we plug in that value with both terms, we get 0069099. If we take away the transverse shear term, we get 0068267. All right. So the difference between these two is in the neighborhood of 1% for this really short stubby beam, 8-to-1 ratio. Note they both scale linearly with force, so this is regardless of the amount of load that's on there, we would get this kind of percent error. Right. The longer we make that beam, the length goes up at a cubic rate in the bending term, right? This one right here goes up with L cubed, and this one only goes up at a linear rate with length, right? Because P is the same, and we're just adding a linear amount of energy with each slice. For the bending, the moment itself is getting bigger as we go down the beam. So the farther we go down there, we're squaring M, and then we're still going down the length. So that's a cubic addition for the bending. So the longer we get, the smaller and smaller this error is going to be. At a really short stubby ratio, if it's only 1%, if we're at a beam that's 50-to-1 or so, it might be down to, tenths of a percent. So that's why we're very often going to neglect this transverse shear term because it doesn't contribute a whole lot to the total value. All right. We do want to keep V of X on our diagram because it's important for passing loads to other members and as well as creating the moment. The shear is often what builds our moment. But it doesn't add up for a fairly short beam, doesn't add up to very much of the total deflection. Sorry. Did that help to illustrate kind of the use versus not use for the transverse shear? All right. Let's see what our next example here is. Statically indeterminate. That's a good one to save for after the break. I'm gonna give us about a 15-minute break today. Let's come back at a quarter after, and we'll crunch through these next couple of examples here and see it used for an indeterminate case. We'll look at a dummy load case where we don't have a load, but we still want to get the value like the rotation on what we just did. And then we'll look at a multi-beam example, and that'll probably take us through the rest of today. All right, so let's come back at quarter after the hour. We'll keep chugging through this slide set. Alrighty, we're back quarter after. After a quick feverish 28 email send out there, I managed to get everybody's exam back to them. Now, for those of you who have been in class with me before, uh, you know the basics of how that works. That's most everybody in the resident section, but of course, everybody in my online section is probably new. So I'm going to go through. Can't really do the specifics of the exam because a couple people haven't taken it, but I'll tell you the format for how I score it, uh, just so you understand. I sparingly will annotate the exam itself, so you've gotten that one back. You'll also get one that's got your name underscore exam scoring, and that's going to be a single column from this spreadsheet right here. So everybody's got a column going across. I've scrubbed all names off of this and whatnot. And what you're going to have in your column individually sent, you'll have the course average that you currently have. That's half homework and half exam one right now. And then down in the specific sections, we're going to have a number of items per problem. Okay, the left-hand column is the weighting of each item. All right, so problem one in total is worth 40 points. That's all these little items over here. And then under your name, you're going to have a column that's mostly ones and zeros, quasi-binary. That's, did you get each of these individual items? Yes or no. You might see an occasional 0.5 or that one item that's 6 points. Somebody got 5 out of 6 on that one, hence the 0.833 rounded up, etc. All right. And then what I do to score these is I just take the weight over here, the number of points for this specific item. It's a formula or an answer or whatnot. I had to scrub that down since we still have a couple people that haven't taken it yet. And then I just do a sum total. I'm told there's actually a sum product sum in Excel, which would have saved me thousands and thousands of typings here. But nonetheless, it's in there, and then I just fill across. So I go through and I grade everybody's problem number one, everybody's problem number two, and I'm trying to make it as consistent as possible so that you don't wonder why I got so many points and somebody else got a different amount. All right. So all that for problem one and problem two and problem three. As you can see, there's not much of an issue. Everybody did really, really well, and everybody's up toward the top. So we probably don't really need to go through it too much. And you've also got the solution itself. So the written out solution. So you got the solutions, your original exam back, maybe with a few notes, sparing notes here and there. And then the scoring key is the main thing, which is going to have the weight on the left, the specific item, and then whether you got it or not in your column under your name. All right. So that's how I do the grading. Should be fairly straightforward to read, but if you have any questions, feel free to let me know. It's quite fun to go through on a 30 column width like this. So I usually split the screen and then slide it over as I go. But I try to make sure it's consistent for everybody. For those of you who haven't had a class with me before, I try to make it as consistent and objective as possible. So next example we're going to look at here is a statically indeterminate structure. All right. We've tackled this kind of thing before with our superposition and also with our beam bending integration method as well. Superposition is another option that we have to work with. All right. So what we can do in a case like this, we can take a slice. All right, we can keep the left side or we can keep the right side. Remember, we set X where we like. What we're going to do in the superposition cases is we're going to pick however many extra reactions we have. All right, in this case, we got 3 reactions and 2 equations to solve them with. So just like before, and for easy comparison with superposition, we're going to treat that right side roller support as an applied load. All right, we'll see how we come out with this one. All right, so I can take a slice. I could keep the left side or I can keep the right side, whichever is going to be more convenient with me. Something tells me I'm probably going to be better off keeping the right side because I don't have to deal with as many loads. And lucky for me, now that we're free of the whole integration method and other things, I can just put X where it's going to be convenient for me. All right. So let's just say we put X from the right-hand side. All right. So now this length is going to be X. I've got my roller that we turned into an applied load P. This is going to be my reaction, right? And then I've also got my distributed load on there as well. Maybe I'll change the color of that just since we got the same letter on there. All right. And that one provides me with an equivalent load right here of P naught times X for any given position X. And it's also at a distance of X over 2. Now, what we need to deal with for internal loads, we've got a V of X and an M of X. We've seen the energy from V of X, not so big a deal, but the shear force, if we need to transfer it to anything else, good to have that one. So we'll just grab both of those while we're here. V of X, I can see, is going against both of these, so it's going to be P plus the little P naught times X. And M of X, also going to be opposed by both the red and the blue load. So we're going to get positive on both of them. Remember, if we draw M the other way and we get a negative, that's okay because we're going to square M later. All right. First, I've got P, and that's got a moment arm of all of X. All right. And then I've also got my force, blue force, P naught X. All right. So I got the blue one here, got the red one here. And then my moment arm on the blue one is going to be half of X. Right. So M of X, we're going to get big P X plus P naught over 2X squared, right? And since we're thinking ahead, we're going to have to square this, all right? So we need to do a FOIL. This times itself. First one, we're going to get P squared X squared. The middle one, we're going to get 2 of this product, all right? So I'm going to have a 2 out in front. That'll cancel with the half. I'm going to have big P times little P naught. You know what? We could make this a R. That's probably a good idea. Let's just call that R for reaction because I'm going to have that in there anyway. Maybe it'll make it a little easier for us. Reaction times P naught. Okay. And then we've got an X cubed to work with and a half, but we have 2 of those, the inner and the outer of the foil, right? And then finally, we're going to have this second term squared. So it's going to be P naught squared. We're going to have a 4th, and we're going to have what, an X to the 4th, right? Everybody buy that foil okay? Checking me? All right. I know at this hour, I don't get too many checks there. That's why I wasn't so sure until you took the test that everybody was paying attention, but apparently you were. So that's great. All right. And our energy, all right, we're going to neglect that shear energy because we've seen it doesn't add up to a lot, especially on a longer beam. All right. So we got integral M squared over 2EI, and we can just pass that half EI out. Right. And then we've got just integral M squared dx on the inside and from 0 to L. So let's collect our stuff and see what we got to work with. R squared X squared. So if I integrate that one up, I'm looking at R squared over what? 3, and we got an X cubed. Right? And then we've got a R times P naught. And then I've got an X to the 4th, so I got a 1/4 in front of that. And then I got this guy over here. I got a P naught squared. It's going to be over 20 now. 4th, and then the 5 comes down to join it, X to the 5th. And all that's from 0 to L. Everything's times X in there, so just plug the L in. It's not too bad. So I got R squared, L cubed, and we're just going to add in this stuff here. So we got 2 by 3, got 6 EI on the bottom. Right. Note, this is the same energy that we came up with for the end load by itself, right? So if I didn't have P naught in there, I still get back to my cantilever energy. So that looks like we're on the right track. Then I've got R times P naught. I've got L to the fourth. And then on the bottom, I've now got 8 EI. And in my last term, I got a P naught squared. I got L to the fifth. And I had 2 and 20. So I got over 40 EI. So here's my energy for the whole expression. It's got 3 terms, okay? It's got a contribution from just R, all right? That's the exact same as the cantilever energy we got in the last problem, right? Should look the same. It's got a term that is a product of the end load and the distributed load, and it's also got a distributed only term. Now, our Castigliano theorem said partial U, partial force to get a displacement, right? And that means it has to be at a specific spot. So we can't take any D energy, D distributed value, okay? So the P naught term can't be used in Castigliano. We can only use the concentrated or single spot point loads. All right, so let's apply this. We're going to take du dr. That's equal to the displacement at my reaction. Now, when we set this thing up, we put that reaction there, but what was there before was a pin, right? So what do I know about the displacement at that spot? What's my displacement on the right-hand side?
0.
Right, just going to be 0. So now the thing I don't know is R. Before I knew what the force was, and I'm trying to solve the displacement. This time, I know the displacement, and I'm going to use that expression to get the force. All right, so let's see how that works out for us. So I got delta R equal to 0, and I'm just going to take the derivative up here. All right, I've got an RL cubed over now the 2 comes down, so I got 3 EI here. Force length squared, force length cubed over 3 EI. We saw that one before in the cantilever case, so we're also still on the right track. And then right here, this is what's going to let us solve for that unknown R, is this cross term. When we squared M, the foil, the OI in the foil, the OI, outer and inner, gave us this term right here. So R is going to go away, but P naught is going to stay there, L to the fourth over 8 EI. Right? No capital P, or no reaction term in there, right? So we can never get a derivative with a term that just has a distributed load, but this one that shares a product of the two, the distributed load survives on its way down here, all right? And then what I find is my reaction force. Remember, we drew that one down, all right? We're going to get minus 3/8, and what are we left with? We got an L cubed and L to the fourth, so it's going to be P naught L. Distributed times length gives me force units, so that's good. All right, and EI cancels on both. So here's my reaction. Note that it's a minus, and that just means that we drew it down, but the actual reaction is going to be up at 3/8 P naught L. Right? And that's the same thing if we look back to our superposition problem that we did with a flat load and a roller support, right? If I go back to my 3.5 slide set, just missing that button. Go back to my 3.5 slide set. Here's my end load. I got a 1/3. And then on my flat load, I've got a 1/8. So I can see that 3/8 is still going to show up here. I add V for the flat load plus V for the end load, and we're going to cancel down, and the force there would be equal to P naught times L, and then 3/8 for the multiplier. So those two blue shaded pieces right there, we'd add together to 0.
Question.
Yeah. In fact,
Why are we
those are
calling
the
it
two things
V
we
in
got
one
from the
case
derivative.
and
Sorry, go ahead.
Oh yeah, why are we calling it V in here, but delta in the other?
It's just a nomenclature. The little script V is what's often used in the integral beam mechanics, where you have a deflection of X all the way across. In Castigliano theorem, we're talking about deflection at a given spot, at some arbitrary spot, wherever the load is. So we usually just use a general delta for that one. But they don't mean anything different. They're just displacement. Little v is always in the transverse direction, and our delta is in whatever direction the load is pointed. Right, so
Okay.
it's just kind of a more of a general description. But in fact, these two terms are exactly what fell out of that derivative. A contribution from both of those showed up for the displacement at the end, and then we just enforced that that displacement had to be zero. So we can see stuff from the basic beam theory coming through in the energy method. Both of these terms were what we got from our derivative. All right, so let's think about one other example here. Let's say instead of wanting the displacement on that end, I want to know what the rotation is for our example number 1B. Right. Well, here, I don't have a moment. I know if I take d energy, d moment, I can get the rotation. So we'll quantify this one later on at the next energy class. But if we don't have the load we need, we can just throw it on there. Okay. So this is going to be called our dummy load method. We're going to put a load on there, then do the energy formulation. And after we get through with our Castigliano derivative, we're just going to turn it back off, set it back to zero. So let's see how that looks and what happens here. We'll jump back over here. We got P. We know from P we can get delta, but let's say that I want rotation. I don't have a moment on there. I'm just going to add one, okay? Just throw it on there, see what happens. So right here, I've got M naught now, and I've got P. My M of X over here, my V of X over here. And I can see that my M of X for that one, if I cleverly just throw X over from the right, it's going to be P times X plus that M naught on the end, okay? And when I square it, we're going to FOIL again. We're going to do a lot of foiling with this energy method. We've got P squared X squared plus 2 P M naught X, and then plus M naught squared. So there's my M squared. Now, the magic of this foiling and putting that dummy load on is I've now got a term that ties together the real load, P, with the dummy load, M naught. All right. So if I take a derivative with M naught, the real load is going to end up in there in this middle term. All right. So let's see what happens with U. Again, integral M squared dx, and we got a 1 over 2 EI out front. So let's see how these come out. All right. I've got a P squared. I'm going to go ahead and plug in L because they're all just going to go up to L. P squared L cubed over 3 EI. There's the same one that we've seen for cantilever. I got this middle term here with an X to the first power. So when that one comes out, I'm going to get a plus P times M naught times L squared. The 2 will come down and take away that. Well, the half will come down and take away the 2. And then on the end there, I've just got M naught by itself. That's a constant. So when it comes up, it's just times L to the first. So M naught squared and L. So my total energy, I got P squared L cubed over 6 EI. And I got P times M naught times L squared over 2 EI. And then I've also got M naught squared L over 2 EI on the end. So here's my total energy that I got to work with. Let's take a derivative with respect to M naught, right? With respect to my dummy load. So we got to leave M naught alone until here. First term, we don't get anything. Second term, I'm going to get PL squared over 2 EI. All right. Remember, this is supposed to equal my rotation theta. And then I'm also going to get this m naught L over EI. So this says basically that my force is going to contribute this much rotation. And if I had a moment on there, it would contribute this much rotation. Because m naught was attached to both of these, and in that m squared, P and M get together, right? Now keep in mind, PL squared over 2EI, m naught L over EI. Thanks to the magic of Castigliano, if we go back and look at the rotation for an end load, sure enough, it's force L squared over 2EI. That's the first term we got in this derivative. And the second term we got in this derivative, m naught L over EI, there it is for the rotation. All right. You're saying, well, why didn't we just do the superposition method? Well, in a simple case like that, sure, we can do that. But in a more complicated case, we're going to be adding up lots of loads. All right. So we've gotten to this point in the dummy load case, and now is where we set m naught equal to 0 back. So this one's going to go away. We never had an m naught load, but my theta is still a function of the real applied load right there. So here's my rotation due to just an end force, all right? We couldn't use Castigliano by itself for that, but if we added a dummy load in there, then we're able to take the derivative and a P times survived in there. So this one, which also matches our end load rotation from the 3.5 slides. So for dummy load, we're adding something to get a value that we want, just a corresponding load or moment. We work through it just as if it were real, and then only after we take the derivative, because we need it there to take the derivative, and we set it back to 0, and we get the value we need. All right, we're going to look at one more example here. Multi-beam example. Now here where we're getting into a case where we can't just go to eFunda or the back of the book and look up the deflections for a structure like this. So, right? We're going to have to put it together a little bit. So let's say we've got some horizontal load P and we've got some vertical load Q that we want to work with, right? So we got a big structure, and this is with 2, but you know, you could expand it out to 3 or 5 or 10 or however many members you have in the structure. And let's say we want to figure out what our deflections are going to be for a structure like this. So I got P to the right and I got Q going up. We're going to have a beam number 1 and a beam number 2. And we're just going to tackle them one at a time, all right? They're just plain old beams from that perspective. So let's cut the first one right in here, and we might as well keep the end, right? Because it's fairly easy to do that. So for number 1, I'll just put an X. You could even call it X sub 1, but we can move X around from member to member as it is convenient. So let's do a free body diagram number 1. Right. So I'm right here. I got Q going this way. I got P going this way. So over here, I can put stuff however I'd like it. Remember, I'm just going to throw them this way so they stay positive, all right? I got an M1 of X. I got a V1 of X. Put X over here. So in this case, I could say that M1 of X is just Q times X. It's the transverse load times that rotation. And then V1 of X is going to be equal to Q also. And I'll put a F1 of X, an axial force as well. That's just going to be equal to P. All right. Now, V we don't usually use in the energy, but it's important because we got to hand it off when we get to this other beam out here. Okay. So if we're going to look at U for number 1, I've got an axial energy. That's going to be P squared L. If I look back to my 6.1 slides, let's go back to the axial bar. Bar subject axial load says F squared L over 2AE. So P is my axial load, P squared L over 2AE. That's an axial energy. All right. We'll skip the transverse shear force energy because we've seen it's pretty small. And then we need a bending energy. All right. This is essentially just a beam with a cantilever because it's rigidly attached to two, and it's got a transverse load Q on the end. All right. So rather than do the m squared, we've already done a load times x squared. Let's just look back at our previous solution. What do we have for that one? Load squared, length cubed over 6 EI, right? For cantilever end. We've seen that one before. Just make that one simple. Right? So I got two on there. I got an axial and I got a bending. Single term for bending as long as I put x from the right like this. Just Q times x and it comes up as a single term right here. So that takes care of all the energy in beam number one. Now we got to tackle beam number two, and we have a couple choices for how to do that, right? Before I go, let's put Q here and P here, and let's write out what happens at length of L, okay? F1 is equal and opposite at P. Q is this way. And then my moment, as I've drawn it, is going this way at Q times L, clockwise at Q times L. All right. So take a quick mental snapshot of this. This is the whole of beam number one. Back here's where it attaches to beam number two. Okay. And there's Q and P out there. Now, when it comes time to doing a free body diagram for number two, I have a few choices. I can take this end and hand off the loads exactly the opposite. Right. So my first option, plug in L for all this. P's going this way, Q's going down, and QL's going clockwise. If it's going clockwise here, and it's welded or attached to this one, I know this end is Q times L. If Q's going down there, it's going up here. And if P's going to the left here, that means this bar is pulling P to the right that way. All right. So I can do a handoff. This is my first choice, handoff. Hand off the loads, right, from this end to the top of beam number two. That's one option. And then I go to town, get force and shear and moment for this one. Okay, so that's one option. Another option is I can do the whole member, get the reactions at the bottom. Okay, so if there I've got P here and I've got Q here, I could see down here at the bottom, I've got Q going down, I've got P going to the left, and then on the moment, these are both the length of L, by the way. My moment, I can write it one way or the other. Let's just say if I write it this way, it's going to be P times L minus Q times L, if I draw it that way. So I can get my reactions, and I can keep the bottom with these three on there as well. Or yet a third option would be to keep this whole thing, the whole L shape, although it gets a little more dimensional at that point. I could do this too. So I have any of these three choices, and I can get my internal load. So I can get them here with the reactions. I can get them here and keep track of both directions, or I can transfer the load and just work with this little slice here. Which one would you guys like to try? They all come out the same. This one? Okay, so let's try it with the reactions. Right? I better transcribe those just to make sure we get what we want. Okay. So down here, I got PL minus QL. I got Q going down, and then I got P going this way. And we might as well put X up here. All right. And then from that, I've got to put in an M2. I'll put that one that way. And then I've got an F2 of X. And then I've also got a shear, which I might as well put this way. All right. So V2 of X is definitely just going to equal P. F2 of X, axial force, is now Q. And then my M2 of X. Well, if I draw it this way, I've got P times X going with it, and then I got going against it this PL minus QL from the bottom. So that means I got P is going to be times, I'm just going to keep it in different pieces because polygon will be a little easier that way. I got PX. Actually, I could do it this way. It's not too bad. P times X minus L. And then I got a plus QL. And unfortunately, we got to square that one. So M2 squared, that's going to give me P squared, X minus L quantity squared. Remember, we're foiling the same thing. Then I got a 2 PQL, X minus L. And then I got a Q squared L squared. Okay. There's my terms. 3 terms on the moment. And then my force squared, just going to be Q squared. So easy enough on that. So when I look at my U for beam number 2, all right, we've done a lot of polynomial integrating, so I'm not going to make us go through that one. Let's just do this one real quick. We got Q squared L over 2AE. There's my axial. I'll skip the shear energy. And then I'm going to have a couple of different terms to work with my number 2 energy here. So we'll just jump over to the 6.3 slide set and get what we came for over there. I'll save us the integration on that one. We set it up and we saw the different ways. All right. So here's U1, what we got from the diagram. Right. U sub 2, we got the Q squared L over 2AE. There's the axial term. Our axial term here was with Q. That one was with P because they're activating different directions. And then this is what that big mess of 3 terms got us. We had one with just Q squared. We saw that one. We had one with just P squared. And then we had the one with the PQL term, the middle of the foils. That one ends up over here. All right. So this is what we've got. And our total energy, there's 6 terms there. We can combine, which one's the combinable one? The P, Q and EI. Here, the one with Q squared L cubed, there's a 6.5. We can add those together, right? 6.5 gives you what? 2/3. So this, the middle 2 terms right here can combine down. These 2 together can combine to make this one. Everything else will just leave separate. So these 2 together, go with that, 5 terms, right? And then we take our displacements, delta P, du dp. PL over AE, we got PL cubed over 3EI, and then we get a minus QL cubed over 2EI. And then if we take our vertical displacement, that's going to be QL over AE minus PL cubed over 2EI, and then we got a plus 4/3 QL cubed over EI. Right. Looks great, but we don't really have a way to just say, yeah, that's right or that's not. So let's take a look at a couple simple loading cases. We'll look at one at a time, and let's see what we think the deformation is going to come up with. All right. So let's think about P load by itself. Okay. When P's by itself, we're going to get basically a cantilever end load. The beam number 1 is going to pull straight across, and that means beam number 2 is going to rotate with an end load. Okay. It's going to be a pure beam, no axial expansion. Right. So it's essentially number 2 is a beam. We know it's going to deflect PL cubed over 3EI. And from the 3.5 slide set, PL squared over 2EI is the rotation angle of that beam at the end. Now, beam number 1 is attached and along for the ride. So it's going to move over to the right by that same amount, PL cubed over 3EI. And then it's going to rigidly rotate by this angle theta, PL squared over 2EI. Meanwhile, beam number 1 is just getting an axial pull on it from P. So its original length was L. Now it's going to go to L plus PL over AE, right? So it already moved to the right by this much, PL cubed over 3EI, and now it's going to stretch by PL over AE. So versus its original length, this top piece up here, number 1, it moved to the right from beam number 2 bending, and then it stretched itself this much. So this is how far the right end moved in that horizontal direction. We're talking about a small rotation, so even though it had rotated a little bit and stretched, we're going to say its cosine is just about 1. Right? So just from geometry, this is what we have for delta P. That's horizontal displacement due to P load. Let's see if those two terms were in what we had back here. Oh, sure enough, there they are. One from bending and one from stretching. All right. Now let's see what the P load did to the vertical displacement. Well, we didn't stretch or shrink beam number 2. The only thing that happened in the vertical is we rotated beam number 1, right? Because when beam number 2 came over, not only did it deflect, but it turned at the end. And it's attached. So beam number 1 rigidly rotates by this angle theta. All right. We'll say that the displacement here, if we treat it like an arc length, can be theta times the length of the beam L. Right. Remember, this is small, so we'll just shorten it to L. Theta times L should just about be our vertical displacement. Right. We know arc length is angle times length, angle times radius, right? So we're going to say that for a small rotation, this is just about a straight line, and it's the displacement. Theta times L. Here's theta, PL squared over 2EI. We times L, PL cubed over 2EI. And sure enough, the only P term in the vertical is PL cubed over 2EI. Oh, and it has a minus sign. Well, we went down, and Q was drawn up. So that deflection that we solved for with this delta Q would have been in the up direction. And if we only pull with P, we expect it to go like this, over and then rotate down. So we would get a negative on delta Q, and there's the minus sign. This is not too bad, but you can imagine if you got 4 or 6 or 8 beams, this drawing's quickly going to become impossible. But right now with 2, we can pretty much show that what the energy formula came up with is what we get. All right. Last one before we go, let's try Q by itself. This will be a little bit more fun. Right. We got Q. All right, let's look at what it does to the base first. We know that Q is going to stretch it by QL over AE, right? We'll hit an axial expansion, right? Because Q is offset, this entire beam here gets a moment of Q times L, okay? So it stretches, but then it also gets a torque and end moment. If I go to 3.5 slide set, QL cubed over 2EI is my displacement. And the way it's torquing counterclockwise, my beam's going to move to the left. So it moved up by the axial stretch. It moved left by this QL moment. That moment is Q times L. So it's basically ML squared over 2EI, right? Where the moment is Q times L. So moment takes away one of those, moment times L squared over 2EI. And then if we look, moment times L over EI. So QL times L over EI. That's going to be, there's those two terms right there. Remember, Q times L is our moment. So QL cubed over 2EI, QL squared over EI. There's my displacement in the horizontal, my rotation angle. Those came from the beam section. Put this in red. So I got displacement from the beam, rotation from the beam, and then axial stretch caused by Q. Now, number 1, without doing anything on its own, that means it's been shifted up by the same QL over AE. It's been moved to the left by QL cubed over 2EI. And then when it rotates, it performs a theta times L rotation. So this theta times the same beam length means it moved up again. So it moved up when beam 2 stretched and when beam 2 rotated. Both of those add up to movement. And when beam 2 deflected to the left, it took the tip of beam 1 with it. Right? And the very last thing is a cantilever load on the end. So there's another force length cubed over 3EI. That's the actual deflection of beam number one. So all three of these together, I got a 1/3, I got a 1x, that becomes my 4/3 term. And then I got this axial stretch from the adjacent one. Those are all going up. So let's see if we got these contributions right here. If I go back, sure enough, in the vertical, there's my QL over AE, the axial stretch from 2. It's going up, it's turning. And then this one goes along with it. And then my 4/3. That includes both the rigid rotation up to here and then the deflection up again. All right. So this term is the deflection and the rigid rotation. And here's the axial stretch from bar number 2. And then last thing, my horizontal, I went back to the left when beam number 2 underwent bending. So I'm going to go back this way with the end of number 1. It's going against the direction of P. So I expect a minus sign on this one, QL cubed over 2EI. And sure enough, oh, there it is, minus QL cubed over 2EI. Now, if we got any more complicated, I probably couldn't draw this out for you, but hopefully this lets you see the geometry of stuff moving around. These are all formulas that we know from 3.5 or from our axial bar stuff. And then we could compare that with the energy method. We see it did come out the same. So no matter how complicated the structure is, we build up the energy for it. We could trust that we're going to get a good answer there. All right. All right, that is going to do it for this week. We're going to be coming back on Monday, and we'll review our axisymmetric homework and our torsion homework. All right. So keep chugging along on those. I'll release those solutions at the end of the week, probably Friday or Saturday, so you have a chance to look over. Make sure you try them before you look at the solution, but that way you can come in with any questions ready to go for Monday. Did anybody out in TV land have any pressing questions while you got me here?